One of the best ways to understand how a reaction progresses is to understand the energy behind that reaction. And to explain this, we often use what's called an energy diagram, which is kind of a weird looking thing at the start, but once you really understand how they work and what they're explaining, it really starts to help you get an understanding of the way that reactions take place. So when we're looking at an energy diagram, what you're often going to see is a y-axis that is potential energy. The potential energy is essentially how much energy is being built up prior to a collision. So as two molecules approach each other, it is very possible that they could collide and react. The closer they get, the greater their potential energy, and the moment they are about to impact each other is their highest potential energy. If that potential energy is high enough, they can change from reactants into products. At the bottom on the y or on the x-axis, you'll often see what's called the reaction coordinate, which is kind of another way of saying time as the reaction progresses. So how far along are those reactants to turning into products? The way that reaction mechanisms work is you always start with a initial point. That point is never at zero because that means that the reactants have no energy. And the reactants always need to have some energy. That's where we always start, is with reactants. Now, over the course of the reaction, you may think, okay, the reactants are just going to go along, and then they're going to, let's say, change into products like this. But the only thing is if you do this, and your products end up over here, then what stopped them from just turning into that in the first place? If this is the way that reaction mechanisms looked, then you could actually walk through a hallway and you would react with the air as you walked and you would just disappear before you got to the end of the hallway. We know that doesn't happen, so we know that there is actually something preventing this reaction from taking place instantaneously and immediately. That thing that stops the reaction from taking place is what we call the activation energy. You actually have to have the reactants collide with a certain amount of energy so that they can transition into a new substance. Once they have reached that amount of energy, they can then drop and turn into the products. The amount of energy from where the reactants start to the very top of the peak is what we call the activation energy, and it gets labeled EA. So EA is our activation energy. So activation energy. That is going to be measured in kilojoules because the y-axis is in kilojoules. At the very top of this peak is another thing that we should probably talk about, and it is what we often abbreviate with a symbol that looks like this, which means the transition state. The transition state is a very, very short-lived substance that is basically the transition from reactant to product. I like to explain it with this diagram. This is actually showing a biological reaction, but I like to give a different example that we all know of. Remember when you were in school and there was that kid who took their pencil and with their pencil, they always bent it just to do it, and it always snapped, and then they never had any pencils, and then they needed to borrow yours for like the rest of the semester. We all know who I'm talking about, right? There's that kid who was always doing that. Well, imagine them taking that pencil and then bending it, and it's really unhappy being bent, and they get it to the point where it's snapping and cracking, and you can hear it, and you can see the paint chips flying off of it. That is the moment where they could either let go and it becomes a normal pencil, or continue forward and it breaks. That in-between state between being broken and being held together is the transition state. In chemistry, it's the transition between reactants and products. It's a midway thing, and it doesn't want to actually stay there. It's an incredibly high energy molecule that is very short-lived. It is also at the very top of the activation energy. It's the highest energy substance throughout the course of the reaction. Now, after that transition state is reached, if you had enough potential energy to collide from reactants to reach the activation energy, it will actually then change into a product. And in this case, in all cases actually, in an energy diagram, the difference between the reactants and the products is what we often call the delta H, which is another way of saying the enthalpy. That is the heat that is either given off or taken in over the course of a reaction. Now, in this specific example, this is what we would call an exothermic reaction. If we think about what that means, therm means energy or heat. Exo means outside or to exit. It means that heat is given off in the reaction. Whenever the products are lower than the reactants, you will always have an exothermic reaction. So if you see an energy diagram where the products are lower than the reactants are, that has to be an exothermic reaction. We can actually also calculate the delta H by taking the number for the products and subtracting it from the reactants. So if we just pretended for a moment that our products were at, let's say, 100, and our reactants were at, let's say, 300, then the delta H for this reaction would be 100 minus 300, it would be negative 200. In an exothermic reaction, the delta H is always negative. So this is what an exothermic reaction looks like, but there are also reactions that actually take in heat over the course of the reaction, and they're called endothermic. Endo means inside, so the heat is taken inside, and the products are at a higher energy than the reactants are. So let's take a look at what that energy diagram would look like. So in an endothermic reaction, you would still have your reactants starting above zero at some point, and you are still going to have them take in energy until they reach a transition state. But when they decrease in energy, the products will actually be at a higher level than the reactants were. Now, if we wanted to find all of the things that we talked about previously, we would have our transition state at the very peak. Your activation energy is still from the point where the reactants are to the transition state. And your delta H is still from where the reactants are to where the products are. Now, if we wanted to calculate delta H, let's just put some fake numbers in here. Let's say this is at 200. Let's say the products are at 300. The delta H is products minus reactants. So 300 minus 200. The delta H would be positive 100 kilojoules. For any endothermic reaction, delta H is always positive. So when you're looking at this, you can always determine if you are looking at an endothermic or an exothermic energy diagram. An exothermic will have a negative delta H and will have products lower than reactants. An endothermic diagram we'll have products higher than reactants, and we'll have a positive delta H. So this is how we read an energy diagram. And in the next video, we'll go through an example about how we can determine information when we're looking at one. So thanks for watching, and I'll see you next time.